An important term for us musicians is resonance. Objects, so to speak, pick up frequencies that fit, depending on their construction, mass, material, shape, etc. Let's watch a little piece from a lecture by Professor Sarah Bolton from Williams College in Massachusetts. She demonstrates that a string can host a specific number of frequencies produced by a device that shakes the spring at an adjustable speed.
We're going to do this with this pink string. Take an object and shake it back and forth at different rates. So we can try shaking it a couple times a second, or we can try shaking it 100 times a second. In general, if we just shake it randomly, it won't move very much. It'll just kind of go, not much will happen, okay? But if we hit one of its resonant frequencies, one of the frequencies at which it would most like to shake back and forth, suddenly, even though we're not shaking any harder, we'll get much more motion. So I'm going to show you that now. So what I've got in the front here is a shaker and the ability to change the number of times per second that that shaker wiggles the string back and forth. So let's just give this a try. Okay, so right now I'm shaking this string back and forth 22 times per second. And even though I love physics, I would claim that this is not exciting, right? Nothing is happening here that a person could conceivably care about. So what I'm going to do now is try to pick some other frequencies to shake this string. I'm going to increase very slowly the number of times per second I'm shaking here, but I'm not going to shake any harder, just faster, okay? Okay. So I think you can see there that as I got up to a higher frequency, this is about 40 shakes per second, 40 hertz, suddenly I get this very much bigger and very distinct sort of arc-shaped motion. Do you guys see it here? So the string's actually going from curved up to curved down and back about 40 times a second. So I've hit one of the resonances of this system. So this guy would like to shake 40 times a second. And you might think that we're done, but we're not. I do say that to my real students in class all the time too. Okay, so let's just keep going. I'm going to increase the frequency a little more. Now I'm up around 45 times a second. 45 times per second is not special to this string, right? It's not doing anything exciting. But I'm going to keep going. You can hear it humming. That's about 60 times a second. And when I get up there, about 80. Interestingly, about twice the frequency. So 40 was special to this string, and now you can see here 80 is also special to this string. It's giving me a different motion, right? This one is stationary in the middle and has two big motions on either side. Okay, it's a different motion, but it's another resonance. Okay, so this string, actually, like all extended objects, has multiple resonant frequencies, not like the pendulum that just has one number of times per second it'd like to slosh back and forth. This one has a couple choices. 40 is good, 80 is good, might even be able to get more. Okay, there it goes. Let's see if we can do more. Okay, that's 120, mysteriously 3 times 40. That one's good too. Right now I've got 2 stationary spots and 3 bumps. And you can imagine that if we all had a lot of patience, we could just keep going here, right? We'd get more and more and more. There are as many different resonant frequencies of this string as you would like, and they all seem to be separated by 40 hertz. 0, 40, 80, 120.
Resonance can have spectacular effects. On a large scale, there is this famous example of a suspension bridge. It is brought in a state of resonance by the wind, so that it actually behaves pretty similar to the string we just saw. On a smaller scale, I think we all know the example of a voice breaking a wine glass. When the straw in the glass starts bouncing, you know that you got the right frequency. And this kit shows that you don't need to be an opera singer to destroy the glass.
Mom, I broke it!
Here is a famous experiment demonstrating how a lot of metronomes all synchronize after a few minutes, again based on resonance. To me, this looks almost like a dance floor. If we let our bodies move on the beat of the music, in a way we resonate. Apparently, that's something people really like. Another feature of sound is that it has crystallizing capabilities. If you put sand or salt on a vibrating plate, it creates beautiful patterns. The sand in fact acts like memory, because when the tone is stopped, the pattern still remains. In water, the effect is similar. These photos were taken by playing a tone in water. The Japanese professor Masaru Emoto investigated the memorizing capabilities of water in detail. He froze drops of distilled water that had been exposed to several types of music, and he discovered that the shape of the ice crystals differed tremendously. This picture shows a crystal of water that has been listening to Yesterday by the Beatles.
Yesterday, all my troubles seem so far away.
And this is the song Edelweiss from the musical The Sound of Music.
Edelweiss, Edelweiss.
Looks pretty much like the real flower, doesn't it? And this comes from water that was exposed to heavy metal music. It looks like the water is confused and the crystal is distorted. So why is this important to us musicians? Well, the human body consists for 70% of water, so music does something to the water in our cells. That's why we can have a great feeling even a couple of hours after a great concert. Or we feel lousy after a concert with music we can't resonate so easily with. Let's watch a powerful animation from this documentary on YouTube on water memory and structured water.
Means how its molecules are organized. We can see how water molecules join together into groups. These are called clusters. Scientists came up with the idea that these clusters work as memory cells of a certain sort, in which water recalls the whole history of its relationship with the world as if on magnetic tape.
This all is food for thought. It makes us aware of the way we transfer music to our listeners. It also clarified to me that in a relative way we can transpose a song to any key we want, but pitch and keys also have an absolute quality. If we take a happy song in E major down to E flat major, it might lose its character because the water molecules in our body react completely different. Knowledge about keys and their qualities existed already in ancient times, like shown in this list. Hopefully this movie contributed a bit to the understanding of this phenomenon.